Introduction. Hello students, let us have a look at our third chapter, that is magnetic effects of current and magnetism. After studying this chapter, you will be able to explain the concept of magnetic field, define the electromagnet and magnetization, discuss the Ørsted's experiment, understand the Biot-Savart law and Ampere's law, explain the magnetic force on a moving charge, understand the magnetic boundary conditions, explain the Earth's magnetic field and magnetic elements, discuss the factors that affect the strength of an electromagnet. Let us now understand what is magnetism. Magnetic field enables much of the technology that we take granted for today. Transportation systems such as the magnetic train in train, power generation equipment such as wind power, hydroelectric systems. In fact, magnetic field affect almost every aspect of our daily lives, enabling today's technology and the technologies of tomorrow. Magnetic field. Let us find out about magnetic field. Magnetic field is a region near a magnetized body where magnetic forces can be detected. Let us understand the concept of magnetic field with the help of an activity. Place a cardboard over a magnet. Sprinkle some iron fillings on the cardboard. Gently tap the cardboard. Look at this now. We observe that the iron filings align themselves in a definite pattern. These patterns indicate the magnetic field of the magnet. A magnetic field is represented graphically by lines of force. Let us now take a look at the mapping of magnetic lines of force. A pictorial representation that gives the direction of the magnetic field at various points in a magnetic field is called a map of the magnetic field. Let us try mapping the field using a compass. A compass is a small magnetic needle enclosed in a brass case with a glass top. Okay, now fix a sheet of paper on a drawing board. Place a bar magnet on the sheet of paper. Trace the boundary of the bar magnet. Now place a compass at your north pole. What do you see? The magnetic needle comes to rest in a particular direction. Mark the other end of the needle as shown. Now move the magnetic needle in such a way that its south pole is where its north pole was. Mark the new position of its north pole. Repeat this until the other end of the magnet is reached. Join the points. You see that these points form a curve. The curved line represents a magnetic line of force. Similarly, place the compass at different points near the north pole of the magnet and then map the lines of force. Now let us see the patterns of lines of force. Patterns due to a bar magnet. Let us now study the nature of magnetic lines of force due to a bar magnet. Place a bar magnet on a cardboard. Sprinkle some iron filings on a piece of paper and place it on the magnet. Tap the paper gently. The iron filings arrange themselves in this pattern. Patterns due to two bar magnets placed with opposite poles facing each other. Place two bar magnets with their opposite poles adjacent to each other. Sprinkle some iron filings on a piece of paper and place it over the two magnets. Tap the paper gently. You see that the iron filings align themselves about the bar magnet. This is a pictorial representation of magnetic lines of force. Patterns due to two bar magnets placed with like poles facing each other. Place two bar magnets with their like poles adjacent to each other. Sprinkle some iron filings on a piece of paper and place it over the two magnets. Tap the paper gently. What do you see? You see that the iron filings align themselves about the bar magnets. This is a pictorial representation of magnetic lines of force. Now coming to neutral points, the space in between two opposite magnetic fields where no magnetic lines of force pass is called neutral point. If a magnetic compass is placed in this space, it does not set in any particular direction. Okay, now let us find out the properties of magnetic lines of force. The lines of force are closed and continuous curves. Outside the magnet, the lines of force are directed from the north pole towards the south pole of the magnet, whereas within the magnet, the magnetic lines are directed from the south pole towards the north pole. The lines of force repel each other and the lines of force never intersect. Electromagnet. Now we shall see what electromagnets are. A soft iron bar is taken and several turns of an insulated copper wire are wound over it. On passing electric current through the wire, we find that the iron bar becomes a magnet. Such a magnet is called an electromagnet. Observe that the iron filings get attracted towards the electromagnet only when the current is flowing through the wire. That is, the iron bar remains a magnet so long as the current is flowing through the wire. On stopping the current, the bar loses its magnetism and the iron filings fall down. An electromagnet is a temporary magnet. The magnetism produced in an electromagnet depends on the amount of current flowing through the wire and number of turns wound on the soft iron rod. Ørsted's experiment. Until the 18th century, the relationship between magnetism and electricity was not that well understood. This all changed in 1820 when a Danish physicist named Hans Christian Ørsted was conducting a demonstration for some of his students. As he was demonstrating the heating effect of current through a platinum wire, he noticed quite accidentally that the needle of the compass on his desk moved each time he switched the current on and off or whenever he moved the wire near the compass. He was baffled. So he started studying this effect further. He speculated that the current in the wire somehow generated a magnetic field on its own in order to have an effect on the compass. Now his publication caught the attention of another physicist, Andre Ampere, who quantified this effect mathematically. Let us now see the deflection. Arrange a battery, ammeter, key and copper wire as shown. Place a magnetic needle below the copper wire. Switch on the key and observe the magnetic needle. Now switch off the key. We observe that the magnetic needle swings when the key is switched on and comes back to its normal position when the key is switched off. The magnetic field around a conductor can be mapped by using iron filings. Let us now trace the magnetic field pattern around a current carrying straight conductor and a circular coil. Arrange a copper wire, reversing key, rheostat battery and a thick sheet of cardboard with a hole at its center as shown. Sprinkle some iron filings on the cardboard. Now tap the cardboard gently to overcome the force of friction and inertia of the iron filings. Observe that there is no change in the arrangement of iron filings. Switch on the current now. Observe that the iron filings arrange themselves in concentric circles around the conductor. This is because the electric current produces a magnetic field around the conductor and the iron filings, being magnetic in nature, align themselves in concentric circles. Now place a magnetic needle near the wire. The direction in which the north pole of the needle points indicates the direction of the magnetic field at that point. Now observe the magnetic field pattern when the direction of the current is reversed. The direction of the current is changed by rotating the arm of the key. What you see is that the needle of the compass deflects in the opposite direction, indicating a change in the direction of magnetic lines of force. Now observe what happens if the current is increased or decreased. On increasing the strength of current in the conducting wire, the number of lines of force around it increases. Let us take a look at the properties of these lines of force. The magnetic lines of force are in the form of concentric circles. The plane of the magnetic lines of force and hence magnetic field is at right angle to the plane of the conductor carrying current. The direction of magnetic lines of force reverses with the change in the direction of flow of current. On increasing the magnitude of current in the conductor, the number of magnetic lines of force increases. In other words, the magnitude of magnetic effect increases with the increase in the strength of current. Magnetic field around current carrying conductor. If the magnetic field generated by a conducting wire can exert a force on a magnetic compass, then the stationary magnet can also exert a force on a conducting wire. Over here we have a wire conducting current in the direction shown and it is suspended in a magnetic field. We can determine in which direction the force will act on the wire by using something called the right hand rule. Why don't you try this for yourself? If you point in the direction of the magnetic field, your index finger, and simultaneously point in the direction of current flow in the wire with your thumb, then your middle finger will actually be pointing in the direction of the force on the wire. So go ahead and try this. Which direction will the wire be motivated to move? Is it up or down? If you answered down, then you are correct. Maxwell's corkscrew rule. Imagine a right-handed corkscrew being rotated along the wire in the direction of the current. The direction of rotation of the thumb gives the direction of the magnetic lines of force. Ampere's swimming rule. This rule states that if a man swims along the wire carrying current such that his face is always towards the magnetic needle with current entering his feet and leaving his head, then the north pole of the magnetic needle is always deflected towards his left hand. Make 2 holes in a sheet of cardboard. Pass a thick insulated copper wire through the holes as shown. The ends of the coil are connected to a battery, a rheostat and a reversing key. Sprinkle some iron filings on the cardboard. Switch on the current. When the current is passed through the coil, the iron filings on the cardboard align themselves with the magnetic lines of force of the current carrying coil. Now observe the magnetic field pattern when the direction of the current is reversed. The direction of the current is changed by rotating the arm of the key. What you see is that the needle of the compass deflects in the opposite direction, indicating a change in the direction of magnetic lines of force. Now observe what happens if the current is increased or decreased. On increasing the strength of current in the conducting wire, the number of lines of force around it increases. Let us take a look at the properties of these lines of force. The magnetic lines of force are nearly circular near the wire, that is, at the points where current enters or leaves the coil. Within the space enclosed by the wire, the lines of force are in the same direction. Near the center of the coil, the lines of force are almost parallel to each other. That is, magnetic field is uniform. At the center, the plane of magnetic lines of force is normal or perpendicular to the plane of a circular coil. The magnetic field or the intensity of magnetic field is increased if the strength of current in the coil is increased. The polarity of the faces of the coil depends on the direction of current and is obtained by a rule known as the clock rule. According to this rule, When an observer looking at the face of the coil finds the current to be flowing in the anti-clockwise direction, then the face of the coil will behave like the north pole. While if the current is in the clockwise direction, then the face of the coil will behave like the south pole. Magnetization. Magnetization is the process by which a magnetic substance attains magnetism temporarily or permanently. The methods used to magnetize a magnetic substance are single touch method, double touch method, electrical method of magnetization. Demagnetization is the process of removing the magnetic property of a magnet. The magnetism of a magnet can be totally or partially destroyed in the following ways: by rough handling, by induction, and by passing electricity. Single touch method. Place a soft iron piece to be magnetized on a table. Take a bar magnet and place one of its poles on the iron piece as shown. Rub the iron piece with the bar magnet. When the magnet reaches B, lift it and place it back to A. Repeat the process several times. The upper side of the soft iron gets magnetized. Now turn the soft iron and magnetize the lower side in the same manner. The point A will get the same polarity as the pole of the magnet touching it, and the other end of the iron will attain the polarity opposite to that of the magnetizing pole. Now test this for magnetism. Place some iron nails on the table. Bring the soft iron piece near the iron nails. The soft iron piece attracts the nails, showing that magnetism is induced in it. Double touch method. Place a steel bar to be magnetized on two bar magnets. Now place the opposite poles of two strong magnets at the middle of the steel bar as shown. Move the magnets towards the opposite ends, keeping the magnets inclined. On reaching the opposite ends, lift the magnets and place them back to their respective original positions. Repeat the process. The polarities developed at the ends are opposite to the polarity of the pole used for magnetization. Now place some iron nails on the table. Bring the steel bar near the iron nails. The steel bar attracts the nails, showing that it has acquired magnetism. Electrical method of magnetization. The bar to be magnetized is placed inside a long coil of insulated copper wire. The copper wire is connected to a source of direct current. When the circuit is closed, a strong direct current passes through the coil of the insulated copper wire and the bar becomes a magnet. The polarity of the rod depends on the direction of the current. If the bar is viewed from one end and the current is found to be flowing in a clockwise direction, then that end will attain south polarity. If the current appears to be flowing in an anti-clockwise direction, then that end attains north polarity. If it is a steel bar, it becomes a permanent magnet. If the bar is a soft iron bar, then it becomes a strong bar magnet and is called an electromagnet. This electromagnet ceases to be a magnet as soon as the current is stopped. Let us see an experiment that shows electromagnet is a temporary magnet. The bar AB attracts iron filings as it acquires magnetic property. Now open the circuit by plugging out the key. The iron filings fall off as the bar ceases to be a magnet when no current is flowing through the coil. Let us take a look at the methods of demagnetization. The magnetic property of a magnet can be totally or partially destroyed by rough handling, by heating, by induction, or by passing electricity. Hammering, dropping, and rough handling of the magnet can demagnetize the magnet. A magnet loses its magnetism if it is heated above a certain temperature called its Curie point. The Curie point for iron is 770 degrees Celsius and that of steel is 880 degrees Celsius. The Curie point for nickel is 358 degrees Celsius and that for cobalt is 1121 degrees Celsius. If two magnets are placed side by side with similar poles together, each induces opposite polarity in the other. As a result, the magnets lose magnetism. To avoid this self-demagnetization, the magnets are placed in pairs side by side with their unlike poles together as shown. Magnetic materials. Now we shall look at the different types of magnetic substances. When we bring a piece of iron closer to a magnet, it gets attracted towards the magnet. Iron and steel are not the only substances which are attracted by a magnet or can be magnetized. In fact, most of the substances are magnetic. Michael Faraday, an English physicist, classified the magnetic substances into three classes, namely diamagnetic substances, paramagnetic substances, and ferromagnetic substances. Diamagnetic substances. These are those substances which are feebly repelled by a magnetic field. Bismuth, lead, mercury, copper, diamond, gold, silver, and silicon are examples of diamagnetic substances. If a lead rod is suspended in a magnetic field, it slowly sets itself at right angles to the direction of the field. The behavior of a diamagnetic substance is independent of temperature. Paramagnetic substances. These are those substances which are attracted by a strong magnetic field. If an aluminium rod is suspended in a magnetic field, it slowly aligns itself along the direction of the magnetic field. Aluminium, platinum, chromium, magnesium, tungsten and calcium are examples of paramagnetic substances. A paramagnetic substance, when placed in a magnetic field, is feebly magnetized in the direction of the magnetizing field. Temperature has an adverse effect on a paramagnetic substance. Due to rise in temperature, a paramagnetic substance tends to lose its magnetism. Ferromagnetic substances. Substances exhibiting strong magnetic properties are called ferromagnetic substances. Iron, cobalt, nickel, steel, alnico, etc. fall under this category. If an iron rod is suspended in a magnetic field, it quickly aligns itself along the direction of the magnetic field. A ferromagnetic substance, when placed in a magnetic field, is strongly magnetized in the direction of the magnetizing field. Again, temperature has an adverse effect on a ferromagnetic substance. Due to rise in temperature, a ferromagnetic substance tends to lose its magnetism. Now let us find out about Earth's magnetism. Earth's magnetism. Now let us find out about Earth's magnetism. The Earth behaves like a powerful magnet. The south pole of this magnet is towards the Earth's north pole and vice versa. Let us now see the experimental evidence to prove Earth's magnetism. A freely suspended magnetic needle always aligns itself in the north-south direction, showing that Earth is a magnet with its south pole towards the north pole of the magnet. A piece of iron can be magnetized only in the presence of a magnetic field. It is found that a piece of iron buried inside the Earth with its axis parallel to a freely suspended magnetic needle in its rest position becomes a magnet. This shows that the Earth is a magnet. Neutral points are observed when we draw the lines of force of a magnet. Neutral points are the points where the magnetic field due to a magnet is exactly balanced by the magnetic field of the Earth. If Earth had no magnetism of its own, neutral points would not be observed. Lines of force are the imaginary lines in a field of force that enable the direction and strength of the field to be visualized. They are used primarily in electric and magnetic fields. Now we shall look at the theories regarding the cause of Earth's magnetism. Sir William Gilbert gave the idea that Earth's magnetism is due to the circulating electric currents near the outer surface of the Earth. The rotation of the Earth about its own axis is responsible for the generation of these currents. Hot air blowing from the region near the equator and moving towards the northern and southern hemispheres causes an electrification of Earth, leading to Earth's magnetism. According to another theory, the molten conducting materials like nickel and iron within the central of the Earth become magnetized due to the currents produced by the rotation of the Earth on its own axis. The third viewpoint is that the magnetism is due to the ionized gases present in the atmosphere. The atmospheric gases get ionized due to the interaction of the atmospheric gases with the radioactive materials and cosmic rays and high energy particles coming from the sun. Thus, a strong electric field is created as the Earth rotates about its own axis around the sun. These currents generate a magnetic field around the Earth. Elements of Earth's magnetism. Now we shall take a look at the elements of Earth's magnetism. The physical quantities which determine the intensity of Earth's total magnetic field completely in magnitude and direction are called magnetic elements. The three elements of Earth's magnetism are the angle of declination, angle of dip, and horizontal component of Earth's magnetic field. Angle of declination. The vertical plane passing through the axis of a magnetic needle suspended freely through its center of gravity is called the magnetic meridian. Similarly, the vertical plane passing through the line joining the geographical north and south poles is called the geographical meridian. The acute angle between the magnetic meridian and the geographical meridian is called the angle of declination at that point. When a magnetic needle is suspended freely about its center of gravity in such a way that it is free to rotate in a vertical plane, then in a steady state the needle dips down with respect to the horizontal. It is being found that in the southern hemisphere the north pole of the magnetic needle inclines downwards, whereas in northern hemisphere the south pole of the needle inclines downward. A magnetic needle which is inclined is called the dip needle. The angle between the axis of the magnetic needle, which lies in the magnetic meridian, and the horizontal direction is called the angle of dip. The magnetic axis of the needle represents the direction of the Earth's magnetic field. Hence, we can define the angle of dip at a place as the angle between the direction of the Earth's magnetic field and the horizontal component of the Earth's magnetic field in the magnetic meridian at that place. Displayed here are the positions of the magnetic needle when placed at Earth's magnetic pole and at the magnetic equator. Okay, so what do you observe? We observe that at the Earth's magnetic poles, the magnetic needle directs in the vertical position, and so the angle of dip is 90 degrees. It means that the magnetic field of the Earth at the Earth's magnetic poles is vertical or perpendicular to the Earth's surface. Now, in the same way, at the magnetic equator, the magnetic needle aligns in a horizontal position, and so the angle of dip is 0 degrees. It means that the magnetic field of the Earth at the Earth's equator is horizontal or parallel to the Earth's surface. Horizontal component of Earth's magnetic field. We know that except at the equator of the Earth's magnetic field is nowhere horizontal. Therefore, at any place, the Earth's magnetic field in the magnetic meridian may be resolved into two components, namely horizontal component BH and the vertical component BB. Shown here is a freely suspended magnetic needle NS. The vertical plane OBQR passing through its axis is the magnetic meridian. The plane OABR is the geographical meridian. The angle between these two planes is the angle of declination. The angle between the axis OQ of the magnetic needle and the horizontal OP is the angle of dip delta. The axis OQ of the magnetic needle represents the direction of the Earth's magnetic field BE. BE can be resolved into horizontal and vertical components BH and BB. Now from the figure we know that the horizontal component of Earth's magnetic field BH is equal to BE cos delta. Vertical component of Earth's magnetic field BB is equal to BE sin delta. Squaring and adding equations we get BH square plus BB square is equal to BE square cos square delta plus BE square sin square delta, which is equal to BE square. Therefore, BE is equal to root over BH square plus BB square. Since sin square delta plus cos square delta equal to 1, dividing equations we get BB by BH is equal to BE sin delta by BE cos delta, that is equal to tan delta. Therefore, delta is equal to tan inverse BB by BH. By knowing the value of theta and delta at a place, we can determine the direction of the magnetic field BE. And if we know the values of BB, BH and delta, the magnitude of Earth's magnetic field BE can be determined. Thus, theta, delta and BH give complete information about the Earth's magnetic field at any particular place. Did you know that the aurora, the streamers of light in the sky above the northern pole or southern magnetic pole, are caused by the Earth's magnetic field? When a fast-moving stream of electrons moves down in the Earth's magnetic field, they collide with gas atoms and emit light. The display of colors that is observed in extreme northern latitudes are called aurora borealis, and that observed in extreme southern latitudes are called aurora australis.